Hello and welcome to this video about theorems and proofs in vector spaces. In this video we'll explore more about proofs involving the vector u and its negative. These are the definitions of vectors that we'll be using. So we'll start with this theorem, which isn't really a theorem or even a corollary, because it's really just an exercise with playing with the axioms, which I'll call a show that, but it will give you insight into how to do these proofs. We'll start with this show that, which is like saying that 1 plus 1 is equal to 2, but these two statements are really different to each other and need to be proven to be true. So we'll start with the left-hand side and separate the 2 into 1 plus 1, which is a property of scalars. We need to do this step so we can apply a different vector space axiom. We'll use distributivity to make it into a sum of two vectors. Then we'll use the property of 1 to eliminate the 1's, so that completes the proof. Now to prove this result, it should become a bit more obvious how to do this calculation once you've had a bit more practice at other similar calculations. So firstly we'll separate the minus 2 into the sum of two minus 1's. Then we'll use distributivity to make it into a sum of vectors. And finally we can use this negative vector theorem to transform this expression into the sum of two negative vectors. We can then prove this show that adding three vectors of the same value together produces 3 times this vector. We can prove this two ways. We can turn 3 into a sum of 1 and 2 like this. Then we can use distributivity to make it into a sum of two vectors. We'll use the result that we just used before to manipulate it like this. Then we'll eliminate the 1 using the property of 1. Then, because vector spaces are associative, we can write it out as 3 vectors without any brackets like this. So now to prove this the second way, we can separate the 3 into a sum of 3 1's like this, assuming a sort of general associativity. We can then use distributivity to turn it into a sum of 3 vectors. And then we can use the property of 1 to eliminate the 1's, thus completing the proof. I'd like to generalize the associativity law so that I can use distributivity to multiply out any number of scalars in the brackets. It's not as necessary here as in the first lot of theorems, but if your teacher doesn't want you to do it, then it's better to do what he says. So now to use vector space axioms to prove this result. We'll start from the left-hand side and use the property of 1 to expand out this expression like this. It's all right to use this axiom in the reverse direction when doing a proof. Then we can separate the 1 into a sum of 2 halves. We can then use distributivity to make this into a sum of 2 vectors, thus completing the proof. Now we can prove this result. N can be any scalar. It doesn't have to be an integer. So we'll start with the left-hand side and expand out the n into being the sum of 1 and n minus 1. Then we can use distributivity to make it into a sum of 2 vectors. And then finally we can use the property of 1 to eliminate the 1, thus completing the proof. Now to prove this result, that nu is the sum of n lots of u. This time n needs to be an integer, and a positive integer as well. So we'll start with the left-hand side and expand out the n to be the sum of n 1's. We'll use distributivity to expand this out to be the sum of n vectors. I think that distributivity is general enough to do this step. And finally we can use the property of 1 to make it into a sum of n u's, which completes the proof. Now to prove this result, which is similar to the last result. Now to begin the proof. We'll start with the right-hand side this time. Then we'll use distributivity to collect all of the n's together like this. It's a distributivity of more than 2 vectors again like last time. So this is the definition of multiplication, so we can rewrite it like this. And so the vector turns into 1 times a vector, which is the property of inverses, or even their definition. And then finally we can use the property of 1 to get this u on its own, and thus we've completed the proof. Now to prove this result, we'll start with the left-hand side and we can substitute a plus negative n in here. Then we can use distributivity to gather everything into this bracket. And so these scalars cancel to give us 0. And so we can use a past theorem to turn it into the zero vector, thereby completing the proof. Now to show this result, it should be easy to see how this can be done by now. We'll start with the left-hand side and use associativity to gather the scalars into the brackets. Then multiplying them out gives us this vector, which completes the proof. And finally, if we use complex numbers as scalars, then we can prove this result. We'll start with the left-hand side and use associativity to gather the two i's into the same bracket. We can write I squared straight away. We can then write -1, which is what I squared is by definition. And then we can use a past theorem to show that this is the negative of u, thus completing the proof. Now to prove that -1 times the negative of a vector is equal to the vector. So to prove this, we'll start from the left-hand side and use the theorem that we've proved earlier to expand the negative of u into -1 times the vector u, being its positive. We'll use associativity to swap the brackets. The two -1's multiply together to make 1. And we'll use the property of 1 to get the vector u all by itself, thus proving this statement. Now to prove this statement, we'll expand the negative vector out to give us this statement using a past theorem. We'll use associativity to gather the two scalars together, one of them being a complex number. Then we'll use scalar multiplication to give us the right-hand side, thus proving this statement. Now for the last statement in this video, we'll prove this statement. We'll use associativity to gather the scalars together, and we can write I squared straight away. The square of I is -1, and then we can use the result at the top to give us the scalar u, thus proving this statement. So I hope that you found this video to be helpful and interesting. Please click like and subscribe if you did. Please leave some helpful thoughts in the comments. Feel free to share this video, and thanks a lot for watching.